Hi guys, now let's have a lecture about database object in GaussDB. This course has two primary learning goals. First, to understand the functions and features of each database object, which will aid us in better planning and designing database in real business. Second, to learn the basic syntax for operating these database objects, providing a theoretical foundation for subsequent database development. In this lecture, we are going to describe the following objects: database, schema, tablespace, user, table, index, view, and sequence. We will introduce each of these objects in detail. Let's start with database. Database is a basic object where we store and organize data. In GaussDB, we create a new database by copying a template database. Once you have installed a GaussDB, there are two template databases, template 0 and template 1, as well as a default user database. When we execute the create database statement, GaussDB will make a copy of template 0. Each client application can only connect to one database at a time. Query among multiple databases in one connection is not supported. Here we can have an example of a database creation. You can see the name of the database, owner, encoding type, and character set used in this database. LCC types specify the character type, which affect uppercase and lowercase letters and digits. By default, it uses the configuration of a template. DB compatibility specifies the compatibility mode of this database. For now, GaussDB supports MySQL, Oracle, Teradata, and PGSQL. And we have two tips when you are going to create a database. First, make sure that the name of a database object does not exceed 63 bytes. Second, we recommend you to change the default database encoding to UTF-8. Then let's talk about schema. A schema is a collection of database objects, and it is used to logically isolate the objects. With schemas, different users can use the same database without interfering with each other. When a user is created, the system automatically creates a schema with the same name as the user. When querying for a database object, the system accesses the schema with the same name as the user first, and then accesses the public schema. To view the search path, run show search path command. Here are some common schema operations. Note that prefixing a schema named with PG underscore or GS underscore is not recommended, because this type of schemas is reserved for system. You can execute the \dm meta command to view the schemas of all users. And then is tablespace. A tablespace is usually used to manage database objects. It corresponds to a certain directory on the disk. A directory can be mounted to a disk independently. Different disks can be planned through tablespaces to store different data. Tablespace is more of a physical concept, while database and schema is a logical concept. From this figure, we can see that a tablespace can contain multiple databases, but in actual applications, you'd better store one database in a tablespace. To sum up, a tablespace is a physical structure and it can contain multiple databases. In each database, schema are used to isolate permissions. After GaussDB is deployed, there are two default tablespaces, pgdefault and pgglobal. pgdefault stores general system objects. It is the default tablespace for storing user table, indexes, temporary tables, and temporary indexes. pgglobal stores system dictionary tables. If you do not specify a tablespace, the data files will be stored in pgdefault. Let's go through an example to show that a tablespace is a directory in the OS. First, we query for all databases in the system. Check their OIDs and the date table spaces. You can see that, except for MyDB3, all databases is in the tablespace 163. Then we query PG tablespace and find out that 163 is PG default. And then we can go to directory of a pgdefault, which is the base folder in root data node path. You can see that several folders named after corresponding OIDs in system. Next, let's look at some common operations for tablespace. When creating a tablespace, you can specify the maximum size of the disk or the absolute path allocated to the tablespace. You can also use the system functions to query and manage the tablespace. For example, call tablespace location to query the absolute path of a tablespace. There are several advantages to use tablespaces. First, if a partition in a cluster exceeds the initial space, you can create tablespace on another partition and reconfigure the tablespace size later. Second, you can store frequently accessed indexes or tables on high-performance disks, such as an SSD, to improve query performance, and store archived data on slow devices to make full use of their capacity. Then let's turn to user and roles. GaussDB users are used to access databases and execute SQL statements. Roles are used to organize and manage database object permissions. You can pack multiple permissions into a row and assign the row to a user so that the user can obtain all the permissions of the row. If the permission of a row are changed, the permission of any user who has inherited the row are automatically changed as well. A user can inherit the permissions of multiple rows at the same time. Here are some common operations for users and rows. When creating a user or a row, you can specify the system permissions, including whether the user is a system administrator, monitoring administrator, or OM administrator. When modifying a user or row, you can modify the system permissions. Also, you can use grant or revoke statement to grant or revoke user permissions on database object. Table are the most used type of database objects, so we won't go into too much about basic usage here. Instead, we focus on several features, like constraints. Only the now, not now, and default constant values can be used as constraints. You can query the pgtable system catalog to view all tables in different schemas, and run the \d command to view the definition of the current table. This page describes table creation operations. You can execute the select statement to copy a table from an existing table, or execute create table if not exist statement to create a table only if there is no existing one. In this way, no error is reported when the table is created. Instead, we can see a notice as a response. You can also use a with clause to set some configure of a table, such as a fill factor. Fill factor indicate that we have reserved some space for data updates in each page. The fill factor of a table is a percentage value between 10 and 100 with a default value of 100, which indicate the full field. If you specify a smaller fill factor, the insert operation fills only the table pages by the percentage specified. The remaining space on each page is used for tuple updating. It gives update the opportunity to place a new version of the tuple on the same page. Therefore, a small fill factor is more appropriate for the table that is frequently updated. You can also execute statements to modify permission on a table, modify the attribute of a column, add a column to a table, rename a column, or add constraints. If you are interested, you can refer to this slide later for hands-on practice. Next, let's take a look at distributed table. There are several data distribution policies for distributed table in GaussDB, including replication distribution, hash distribution, and range distribution. For hash distribution, the distribution column must meet the following requirements. The value of a column are discrete so that the data can be evenly distributed for each data node. You can select the primary key for a table as the distribution key. For example, for a person information table, choose the ID number column as the distribution key. inappropriate distribution key may cause data skew or poor I/O performance on certain DNs. Generally, a difference of more than 5% between the amount of data on different DNs is regarded as a data skew. If this difference is over 10%, you'd better choose another distribution key. Similarly, we come to partition table. Partitioning refers to splitting what is logically one large table into smaller physical pieces based on the specific rules. So logical table based is called a partition table, and the physical piece is called a partition. All data is stored on these physical partitions instead of the logical table. Partition tables are different from distributed table. Distributed tables are based on the inter-shard distribution policies in distributed system. Partition table can be created regardless of whether the systems are distributed or centralized. Common forms of partitioning are similar to distribution policies, like range partitioning, hash partitioning, and list partitioning. Currently, row store tables support all partitions policies. Column store tables support only range partitioning. Let me briefly introduce the aforesaid concepts. Range partitioning is to divide partition columns by range and store data in specific range of the corresponding partition. Hash partitioning evenly distributes data specifying partition numbers. Hash partitioning is performed on I/O devices to ensure that the size of their partition are the same. For example, the data in the material transactions table is hashed and stored in several specified tablespaces based on the transaction ID. In list partitioning, a column has only several values. For example, to create a table based on the region code and province information, you can use list partitioning. Here shows some example for operation of partition tables. When creating a partition table, you can use the partition by statement to specify the partitioning type. Of course, you can also create a level 2 partition, which is called subpartition. The right part shows some operations on partition tables, such as deleting, adding, merging, and splitting. Indexes are also very familiar database objects. An index can be regarded as a dictionary, which is a sorting structure. When searching for data, the system automatically determines whether to use indexes. Indexes are used only when the system considers that an index scan is faster than a table scan. Well, you may ask, which column should we create index? First, columns have filter criteria of where clause, especially scope criteria. Second, column used in join condition. For a query on joined columns, you are advised to create a composite index on those columns. Third, columns that often appear after order by, group by, and distinct. Discarded indexes need to be deleted as soon as possible because they occupy space and increase maintenance cost. Here, we mainly talk about some row store indexes. B-tree indexes use a structure that is similar to the B-pos tree to store key values, facilitating index scan. B-tree index is suitable for equality queries and range queries. Gist indexes are suitable for the set data type and the multi-dimensional data types, such as geometric and geographic data type. Gene indexes are reserved indexes and can process values that contain multiple keys, like arrays. UB-tree indexes are multi-version B-tree indexes used only for UStore tables. The index page contains transaction information and can be recycled. Here we mainly introduce B-tree indexes, which is the most common index. The figure on the right shows the structure of a B-tree index. We can see that there are 3 layers and the leaf nodes point to specific pages. GaussDB supports the following indexing method. Unique index, which refers to an index that requires the uniqueness of an index attribute or an attribute group. If a table declares unique constraints or primary keys, GaussDB automatically creates the unique indexes for the column. Currently, unique indexes only support B-tree index. Composite index, which refers to an index that can be defined for multiple attributes of a table. Currently, composite index apply to B-tree indexes in the GaussDB, and maximum of 32 columns can share a composite index. Partial index can be created for a subset of a table. This indexing method contains only tuples that meet the condition in expressions. Here are some statements for creating index. You can execute create unique index statement to create a unique index, or execute the alter index statement to modify an index. Next, let's look at the views. Views are virtual tables exported from one or more base tables and can be used to control user access to data. A view is equivalent to the query statements of one or more tables. There are two types of views: regular views and materialized views. Regular views store only the definition of views and do not store data of views. The data is still stored in the original base table. Materialized views store query result in the disk to improve query performance. A materialized view stores results like tables, but cannot update data like regular tables. You need to run refresh command to obtain updated data from the base table. Of course, we can also create some scheduled tasks to periodically update materialized views. Here are some basic view operations, such as creating a view, query a view. Check its definition using the pg-get-viewDiff functions, refreshing a materialized view using the refresh materialized command, and deleting the view using the drop command. The last part we talk in this lecture is sequence. A sequence is a database object that generates unique integers according to a certain rule. A sequence is usually used as a primary key. There are two common ways to create a sequence in GaussDB. One is to set a data type of a column to an integer sequence. A sequence will be automatically created by the database for this column. The other is to execute the create sequence statement to create a sequence. Set the initial value of the next value function to the default value of a column. Therefore, this column can be used as a unique identifier. Here are some examples of how you can use sequence. You can execute the create sequence statement to create a sequence, execute the alter sequence statement to modify sequence attributes, or use next value functions to increment a sequence and return the new sequence value. On the right, examples of two ways to set the data type of a column to an auto-increment sequence. The first is to set the data type of a column to an integer sequence. The second is to manually create a sequence and specify the data type of a column as a sequence. To summarize the lecture, we introduced 8 common GaussDB database objects and their basic operations. I hope you can practice by yourself after class to deepen your understanding, which will help a lot. If you want to obtain related documents mentioned in this course, or are interested in some certain parts, visit Public Cloud official website to obtain official documents for more information. That's all for today's lecture. Thank you for your participation and attention, and hope you have a good experience with GaussDB in the future. Thank you.